I want to determine the actual force on this node or on this, imagine there's a bolt going through there and there's 5 pieces coming together. All right, so there's 5 pieces of whatever material. First, hypothetical, say a piece of wood, and we're connecting them with a bolt that goes through all pieces of wood. This piece of wood has a force applied this way. They're all pulling out from that member. So what we do is we take a look, and we have to look at the sum of the forces in the x and the sum of the forces in the y to look at what the overall force felt on this location is. The reason we do this is to determine if the bolt itself is enough to withstand the force being felt. And then what you're going to do is you're going to compare the answer we get to the maximum shear stress of the bolt, or tensile stress, depending on which way the load is applied. In this case, it would be shear. You remember what shear was from yesterday, or from Friday? Shear was?
It's when you have like 2 building forces on the same member, such that if it were to fail, it would fail,
Perpendicular to the?
perpendicular to its axis.
Axis, very good. Perpendicular to its axis. So, imagine a bolt, my arm is a bolt, okay? There's a nut at the end of the bolt, screwed in, there's wood here. If there's a force applied perpendicular to the axis of the bolt, it's called the shear stress. That was one of the things you picked up on from that applet when the object was pulled like this. If it's rotated, right? Imagine like an Indian burn. You have something in their arm. Have you done that before? You ever burn? Whatever they're called? You know?
Yeah.
That's torsional stress. Torsional stress. I know, it's not right out PC, but we'll get over it. So, torsional stress for now, politically correct. If I pull on a member, that's tension. I push on the member, it's compression. Was there another one I gave you guys? I think there was a bending also in there. Where the force is applied only on one end of it. Okay. Anyway, let's go back to this and calculate the forces. So, take a look in the x direction first. Which of these forces is acting primarily or only in the x direction, I should say? 250. See the 250 pound force? That's acting in the positive x direction only. The positive x. So we say the sum of the forces in the x equals 250 plus. Then we have to go to each of these forces and identify, is it acting to the right or to the left? And then we have to think about the fact that we're looking at the x component only, so we have to look at only a fraction of that force using our trigonometric function. The 300-pound force is acting to the right or to the left? I know it's acting up also, but to the right or left? To the right, so you put a plus sign there. So this is going to be 300. But what do we have to do? Yeah, good. Cosine 55. Okay, Henry remembers from physics last year that if I want to find the x component of force, just take the force itself times by the cosine of the angle between the force and the x-axis. So here's the angle right here, 55. So take 300 times cosine 55. Remember, it's always going to be cosine for the x direction and y and sine for the y direction, provided we're looking at the angle between the x-axis and the force. And I'll show the difference at the end there. What are the
What's the symbol in front of the f of x?
Sum. The sum, like summation. It's a sigma. Next, what about the 200-pound force?
Minus.
In the y direction it's minus, but we're looking at the x direction right now. You're right, in the y direction it's down. It's still to the right, isn't it? It's down, so it's negative in the y, but in the x it's still to the right. But what do you have for numbers from the f? Plus 200.
Would this be another sign?
Oh, we're looking at the x direction still.
So it's just
No.
no.
It's still another thing, but it's not sine.
Cosine.
Cosine. And the angle is 65 degrees. So that's that part. So we've gotten 3 of the forces down, right? We've looked at the 300-pound force, the 250-pound force, and the 200-pound force. This is only in the x. Component of this is in the x. A component of this is in the x. All positive. But we have some forces acting that way now. So we have to consider them negative in the x. So next we take a look at the 310-pound force. This is acting up in the y. So for the y sum, we're going to have positive. But for the x, it's acting to the left. So this is going to be a negative now. So we've got negative 310 cosine of 30 degrees. Again, the negative is all one line still. I'm just running out of room. Okay, this is all still one line. The negative is indicating that this force is acting to the left. And then the 275 again acts down, but also to the left. It's pulling this way at an angle of 25. So we still have a minus because it's acting to the left. 275 cosine 25 degrees. Go ahead and tell what you get from that, please. Make sure you're in degree mode. You're probably in radian mode from pre-calc, so change to degree mode real quick. Negative 11.106, so 1111, I guess that makes sense. All right, so what does this tell me?
The negative has more impact on the net. Or
Yeah, on the node, yeah, very good. So it means that the members themselves have an overall net force that's applied to the left. So which way is the reaction going to be from the poles to make this equal and opposite?
Negative.
So yeah, if again, to the left, there's more force acting on this than there is to the right. Are we sure, by the way, that is? Yeah, because the angles, that's why, 55 and 65 are larger, cosine. So to the left, there's more force. So what you see in the diagram is this. Here's what you would see. If you were identifying the node and looking at the reaction forces on the node, you would say this. It's got a reaction in the x direction of 11.106 newtons. And by reaction, I mean what would cause this to be in equilibrium, right? The node or the bolt is pushing back to the right, so that this is in a state of equilibrium. Okay, again, with mechanics and with statics, if things aren't moving, a lot of the time you are in a state of equilibrium. It may not be, though, if there's some sort of vibration, right? And the system might move a little bit and oscillate, you get some increasing and fluctuating forces that it'll feel. But assuming this is stationary, I'm drawing a node here, Rx is to the right because it's opposite the overall force felt by the members. It's a reaction force, okay? If I push against the wall, it pushes back against me. Remember normal force? Okay? So think about if you push against something, Newton's third law says equal and opposite. For some of the force in the y, try and calculate it on your own now. Do it the exact same way. Instead of cosine, though, use good. And if it's up, it's positive. If the force is acting down in any way, it's negative.
You also have to change the angles though, because you have to see, don't you have to see how far off the y-axis is?
No, that's the thing. So then that's what I'm going to point out at the end. If you were to use the angles from the y-axis, you would still use cosine there.
Okay.
That's one way that you'll see if you go on to study mechanics or engineering, that some teachers will teach all with cosine, and you use the nearest axis, and you can do that. But that's the reason being, if you think back to pre-calc right now, cosine of 30 equals sine of 60, doesn't it?
Yes.
So if right now, instead, say I use the sine of 65 here, because I'm going to do the y component, I could have used the cosine, like James was saying, of 25. It's complex, okay? That's because those are co-functions, if you remember. Those two.
So I don't even
Is
need
there
to
any-
find the angles for.
Is there any difference in merit between the two methods? though?
No, but at certain instances, one may be easier than the other. So it's good to understand both. But there's no, in this case, definitely not. But if you're looking at three-dimensional forces, sometimes it's easy to use only cosine. And you just go to the nearest axis. The nearest z, the nearest x, the nearest y-axis, because it's three-dimensional.
What angle is 250 at? Why? So do you not have it? You don't have it.
Think about it. It's only in the x, right? That's why we said the full 250 is in the x. A component, a component, a component, a component. Okay? So for the y, you're going to have 4 parts to it.
I'm not sure if this is right, but I got 353.
Which way? Positive or negative? Did others get positive 353? I'm going to write it out, see if we have the same writing. All right, so I'm going to have 300 sine 55 from the upper right one. Then we're going to have 310 sine 30 from the upper left one. Now, Scott, make sure you didn't use the same negative and positive signs. Or anybody, you guys got two different answers, but make sure you don't use the same negative and positives from the x direction. Because clearly, take a look. These are both positive forces up here in the y. Although in the x, this was negative, right? And this was positive.
310 at positive.
So yeah, these are both positive. No, these are both positive. 310 is acting up and left, so it's positive y. 300 is acting right and up, so it's positive y. These are negative y right here. These are negative in the y direction. So we're going to have minus 275 sine 25. Again, I'm just running out of room. This is all in one line. Right? And then another negative 200 sine 65. Again, using these as negatives because this is acting down at an angle of 25. This is acting down at an angle of 65. So these are both negatives here. What do you got? Negative 94? 94. Sky, you want to check yours?
Yeah, I'm checking.
Please verify others.
All you have to do is put in the sign
Exactly. And the only other thing, though, Ev, is you have to remember that
and signs.
Oh,
these are positive in the y direction, right? Because they both act up.
With the,
These are negative in the y direction because they both act down. But when it's the x direction, these are positive and these are negative because this acts to the right and this acts to the left. So depending on which way you're looking, if you're looking in the y direction, it's vertical. So it makes these positive because they're both acting up. Makes these negative down
and you just eliminate 250.
because it's only acting in the x direction. It's not at an.
yeah, that's why I got it wrong. I had 250 right.
Ah, the 250 was in there. Okay.
But why do you put 250 in when you're using cosine?
I really don't. I use 250 in the x direction, you mean, right?
Yeah, I mean,
Which way is
why do we use the ones going up then? Like the ones at the angle.
Because 250 is only in the x direction. Look at it. Look at your diagram. Look at your diagram. Look at 250. 250 is literally on the x-axis. So it's only acting in the x direction. It's not acting in the y direction at all. The things that are acting in the x and y direction are the other four forces. See these four forces? 1, 2, 3, 4 are all acting at arbitrary angles.
Yeah.
So you have an x and a y component. Think about it. If I wanted to move this desk, I'd probably just push on it like this, right? Push at an angle. I wouldn't crouch down and push some horizontal. This is applying a force in the negative y and whatever x that is considered. Positive, I don't know, depends on what direction I'm looking. So those four forces, 300, 310, 275, and 200, are at angles.
So if you were to like plot it out and it had 0 at that position, then you would just eliminate it.
And it's 0 at that position?
Yeah, like if it was like 5 0. I mean, no 0 5.
Oh, plotted out. Yeah,
Yeah.
exactly.
Yeah.
So if you plotted the coordinate 0, 5, that's on the y-axis. So that would be only a force on the y-axis. The coordinate over here at 5, 0 would be only in the x direction. But the idea is this. Just look at the force. This force right here points perfectly along the x-axis. So what's the angle between, look up please, what's the angle between this force and the x-axis?
There is a 1.
So what is it?
0.
Okay, what's the cosine of 0?
1.
So in reality, very good, Ev. Since the cosine of 0 is 1, this is really 250 cosine 0, isn't it? But cosine 0 is 1, so this is just 250. Ready? Stay with me. Down here, there's really a 250 sine of 0. Well, what's the sine of 0?
0.
It's 0. So I didn't include the 250 down here. That's another mathematical way you could think about it. Technically speaking, you could put cosine 0 right here, where that arrow just was drawn in. But cosine 0 is 1, so this still remains 250. Then you could also put a 250 here times the sine of 0. But that becomes 0, so I don't really include it. And the other way to see that visually is to look at the axis and say, well, this is literally acting on the x-axis, based on our diagram, obviously.
So
94.2?
No, I think it's 103.
Yeah, go
I think it's 103.
Okay.
No, I know.
103?
Yeah, 1264.
Was that a number, like, I don't understand.
I don't know. I've heard like 4 different answers. So I'm not sure which one was right.
6.4.
Point 264? Oh, I heard 1, 2. Sorry.
Which one's right?
264? All right. Now, what does that mean about this node? So let's again reiterate this.
It's going up, this child.
It means that the force applied on the node is up.
Why is it newtons? No,
Oh, it's in pounds. I'm used to being a physics teacher. Sorry, guys. It's not. It's definitely not in newtons. It's in pounds. I know. I gotta fix it. Guys. I teach physics every. We always use newtons. I'm forgetting, of course.
You should screw them up on the next test and just use pounds.
Pounds? No.
Yes.
I don't even know if people recognize that newtons and pounds are really the same measurement of units. Just different numbers or different systems.
You can convert from newtons to pounds.
Can you convert? You could. An easy way to convert is from kilograms to pounds. I mean, you could also do it the other way, but kilograms to pounds, there's 1 kilogram is every 2.2 pounds. So theoretically, a kilogram is 9.81 newtons. So 9.81 newtons is 2.2 pounds. You can do that.
Decided to make another system. Like,
Well, there's been 2 systems forever. I don't know. I mean, I know that the one is the English system. That was one that we traditionally use in England and Australia, I think, use it also, or New Zealand. But like every other country uses the standard international one, SI
that's
units.
okay.
I almost said SAE, which is English ones. All right, anyway, the forces felt, again, are in the negative x and the positive y. So this bolt, okay, because it feels a force in the negative x from this, has to push back, again, in the positive x. We wrote this a minute ago. I'm just reiterating. Okay, 11.1 pounds. And this bolt also feels a force in the positive y, so it has to push back down in the negative y.
Is there a relationship between the amount of pounds and the angles that we figured out? Like why, like 310 is the largest amount of pounds we have, but it's also the direction the line is. Oh no, it's not. Never mind. Wait, actually.
Keep asking, because I at the beginning,
Is this the opposite of the direction the 310 comes
yes.
from?
Oh, no, it's the opposite direction of whatever the resultant we got was.
Okay.
Okay, so again, the overall force felt in the y was positive 103. So the bolt, in order to react to that, has to push down with negative 103, or just push the arrow down.
Yeah, like these are the two opposite of the most amount of pounds that we have.
Oh, it might have happened to coincidentally do that. Yeah. It's the force itself and the angle that matters. So if those angles had changed, it could have been different. Yeah. So in the y direction, the bolt, although I'm not writing negative here, this is really a negative force because I drew it which way? Down. So the bolt is pulling back down and the bolt is pulling to the right. Okay, again, because the overall force from the members was up and to the left. Okay, it was positive and left, so the bolt pulls to the right and then down. We call these again reaction forces. Something that we didn't really talk about in physics. We talked about forces, but we never looked at reaction forces. Reaction forces, again, are where members are joined together. So there are reaction forces everywhere. For example, this cabinet.
What?
It seems very simple, right? The weight of the cabinet is pulling on both of these hinges. These screws right now are under some sort of shear stress. Watch, I'm going to pull on the cabinet. I'm not going to pull too hard because you never know what can happen. But I'm pulling down. So that's causing a force down across the axis of the screw. Here's the screw axis, right? Look at the screw. So the screw is like this. I'm pulling down on it. So I'm pulling down on this bolt. So I'm causing a shear stress. So this screw that's here and here and here and here and this little junction right here, if the weight of the cabinet is pulling down, the cabinet door, it means that the reaction at this junction here is pushing back up for sure. Okay? Use common sense sometimes with gravity, but for this example, it's the same idea. So these might be the overall forces felt in that specific bolt or screw. You need to understand this because if you think about it, when you get to designing your trebuchet, you want to consider the amount of force that's going to be applied. You're going to be using a cylindrical metal rod as your axle to pivot about. So when your lever arm whips around and there's a counterweight pulling, it's going to apply a certain amount of force. You have to think about the fact that that's going to be in a little bit of bending there. Okay, so consider this when you're looking at, for that and for even your bridges when you get to the bridges. We're going to do a bridge project. So an important part here is looking at the nodes and seeing how much force is on each of them. All right. Let's talk about, also look at some quick interactions or like different animations. So a moment is really what we talked about last year as a torque. Okay, a torque is really a moment. A moment is thinking about a force and its distance from the actual axis about which it rotates. So if you think about it, let me give an example of a moment or something where there's moment applied. Okay, right here. So this little tray to the right of the podium has an arm underneath it. I can remove.
Like an airplane.
I can apply force, and it's down, right? When I lift it up, it clicks in, it locks. All right. Now, currently there's very little force being applied to this hinge, but the minute I put something on here, okay, it's a force at an angle. So at a distance. Sorry. So by default, so this bottle, imagine this is the axis of rotation right here. It's hard for you guys to see, so if you need to like lean over or move around. So here's the axis about which is rotating. This bottle is further away from the axis, so it applies more torque. Now it applies less torque, and less, and more, and less, and back and forth. The idea, as you get further from the axis, your torque is increased. Now, that's the reason why sometimes you might want to use a tool like a wrench, and it might not work. So if you use the wrench, and the wrench, let's say for the sake of this, maybe we'll open this up.
I've used that.
Oh.
You'll have to use wrench. Yeah. I want to mention the torque wrench.
I meant like for the chair.
I know, but I returned it to my torque wrench. So I'll give you a sample of the ratchet. Same process as a wrench. Okay?
You're a ratchet.
So-
ratchet.
I make ratchet, I can make push.
So you.
Do you follow Ratchet Girls on Insta?
It's not just me to talk to them.
Let me do that. Sorry. Alright. So, depending on the direction you want to turn something, you're going to adjust this little lever on the back here. Okay? Now, your hand is held at a certain distance from the axis of rotation. This would be a hexagonal large bolt or nut on the end of here. Okay? So you put it on the end of the bolt or the nut, and you want to rotate it. So maybe you want to rotate and tighten it. So you push down, tighten, come back. Push down, come back. That's why a ratchet is a very useful thing. Because you don't have to sit there and rotate with a wrench like 35 times. If you were tightening something completely, you don't have to sit there rotating it over and over. So you tighten it, go back. Tighten it, go back.
And for lots of machines, there's no room to go full circle.
Correct. You have no clearance. So that's why you use them. So if a mechanic comes to fix like a wash machine or something in your house usually, in like a tight confined space and stuff, they'll definitely have a ratchet set because wrenches aren't really useful in that circumstance. Now, if I were to apply a force on this at this location, it's very difficult to apply force downward from here. I don't get a lot of leverage, but the minute I apply force here, it's much easier. You can literally, I can hold my hand enough resistance to withstand my finger pushing here. But the minute I'm out here, there's no way I can do it. You apply much more torque, because again, torque is the product of the force you push with times the distance from where it's rotating. So this distance is like an inch. This distance here might be like 8 inches. So you're pushing down here, this product is much larger than this product would be.
This is just like a wheelchair.
Yes, that's a great, good. It's a great example of yesterday. Remember the wheelchair yesterday? Okay? You guys might have been upstairs when we were looking at it. There was a wheelchair on the second floor, and they were demoing First one. And then when if you push with the wheels, how hard it is, and then you have these levers that you can pull back with, and then push. And you have a lot more torque on it because you push at the end of it. And what we noticed was as you move your arm down, you make less and less torque. There's a lot of deal. This is annoying because it's in the back of the heater. I figure out a better way to hold the starters.
In the box.
I know.
You have so many merchants.
I want to keep them size. What? You get more spring to it.
Yeah.
Oh yeah, I think so.
It's also like,
Sorry. Yeah, it is like one. Yes. It's the lock so you can reverse and go forward and back. And this is a piece, guys. If you needed an extension, so let's say, right, you needed to use a ratchet, no way not at all. Say you needed to use a ratchet, but the bolt was not here. The bolt was here, it was hidden. You couldn't access it. Right? Say you want to get this close, but the bolt wasn't here. You use this extension piece right here, put this on the end of it, then you put the head of the actual socket on the end of here. So you get distance off of here. So you could actually be out here, turning this, and actually have clearance all the way as far in. It was a very useful tool. Anyway, good example for torques and moments. That's why I want to. By the way, completely different, like side note. If anybody's interested, maybe like a weekend project wants to come in and help me out. I got like a peg in here. Yeah. I got like a pegboard for our cabinets to hang tools and stuff. All that stuff needs to be installed though. So I need to do it over one random weekend, but it's a tough job to do by yourself because you need someone to like hold it as you're installing screws and different things. So if anyone's interested, maybe.
money?
No, just to come in to learn about like tools and stuff. I'm not getting paid for it, so I come in on my own time to do this stuff. You find enough. Everybody does finance class. The last thing you need is extra credit. Please, it's for learning. It's for learning.
That the metric system is actually the preferred system of weights and measures for the United States Trade and Commerce, because in 1975, U.S. Congress passed the Metric Conversion Act. But everyone in America said no, so we don't use it. That's why.
Makes sense. It's unfortunate, but I believe what you're saying for sure. All right, so let's talk about a fixed end moment. Let's talk about what's called a fixed end moment. A fixed end moment is this. You have some reaction moments that are developed where the beam member and the actual structure meet. So imagine, please, draw a little building. Here's the ground. Make believe it's Loyola. Let's draw the flagpole coming off Loyola. Here's the flag hanging again. And there's the chain that holds it. Oh, I don't even. We've got 6-7, 6-8, and 7-1. What was 6-5 all about? What was 6-5 all about? Luca. Yeah, equations with radicals. Personally, I think that 6-5 and 7-1 are the harder parts of this test. If there was something to focus on, I'd focus on those for studying. I mean, you need to know 6-7 and 6-8, obviously, but I think those are easier because the idea of conjugates and complex conjugates is analogous to what we've done with binomial conjugates. So it's really not much different. So 6-5, give me an example, Rob, for 6-5. Make up your own example. Luca, make up an example for 6-5. Think it over again. Needs to have variables, Luca. Very simple, okay. What's the answer? What's x? 3 or? Or -3, good. So Luca gave us the easiest possible example ever to start. Perfect. All right, let's go with another example for 6-5. Give me a harder example. Yes. Oh, geez, I'm sorry, guys. Somebody said 3 and I thought right away. Duh. Square both sides. All right. I apologize. Let's come up with something more complicated. It was too easy. That's why, Lucas. Sorry. Come up with something where you have x and something else under the radical.
Radical 5x plus 17 equals 3.
All right. And let's put something else involved too. Give me one more thing. So we have to do a little more than just square.
Like on which side?
On the left-hand side.
Put a 2 in front.
All right. Let's do that. So we got 2 times the quantity, square root 5x plus 17 is equal to 3. So what was the first step when solving radical equations? Because the other one earlier, we didn't have to do the first step, really. First step for solving radical equations?
Don't you make the radical?
Make the radical alone? What's another way to say that? What's the word?
Isolate.
Isolate the radical. Very good. Isolate the radical. So divide by 2. Start by dividing by 2. Let's go. So we've got 3/2 equals radical 5x plus 17. How do we get rid of the square root? We don't make the mistake I made a minute ago. How do we get rid of the square root? Square it. Square both sides. Oops. Yielding on the left-hand side still 5x plus 17. What about the right-hand side? 9/4. Again, remember squaring both the numerator and the denominator when we square. After that, what do? What's an easy way to solve an equation if we have a fraction involved? I hate fractions. I don't want fractions. What do? Hey, you can start by multiplying everything by 4. That works. Simplifying things much easier for me now. So I get 20x plus, we have 40 plus 28 is 68 equals 9. Get rid of the 68 by subtracting it. We're going to have -59. Oh, this would have been nice if it worked out. So close. It was 60, right? And then as a result, what do we get? A number that is close to 3, but not exactly 3. All right? How do we know that we're right, Sabine? How are we sure that we're right? What do we do? Very good. I'm not going to waste time right now, but you substitute it into the original. And recall that you don't manipulate the right-hand side of the equation. You don't, or the left-hand side. You don't move things, remember? When you substitute in a check, you have to leave things on their sides of the equation. So for example, remember how we started by dividing by 2? When you're checking this and you plug in the number into the original, the 2 remains on the left-hand side of the equation, outside of the radical. You don't start by dividing by 2 instead. All right? Try one on your own. Let's do one on your own now. Oh, geez.